Okay, we're going to start with the first lecture in Unit 5, and it says, "It's not hoarding." It says, "I'm positive I've lost an electron. I better keep an eye on that." And so we're going to talk about um, ionic bonds and how they're formed and everything else. Our learning goals for this lecture, students will construct electron dot diagrams for elements, consider the reasons for ion formation, predict the stable state or the stable form for ions, and understand the formation of ionic bonds and the resulting properties. So essentially what we're going to do is we're going to look at the valence electrons and look at how they affect bonding, and specifically how they affect in ionic bonding. So what we already know coming into this, electrons determine reactivity. So when we're looking at this, our valence electrons, and when we talk about electrons in chemical bonding, we're always talking about valence electrons. Those determine how reactive something is. And atoms in a noble gas column will not react. So we know that the noble gases do not react because they already have 8 valence electrons. And so they don't need to bond with anything to become stable. Now, what we learned in the lab, that ionic substances have very high melting points. They have a crystal structure that's very organized, and they conduct electricity. And this is what we should have pulled from the lab. Now, jumping into the lecture, the first thing we're going to start with is the octet rule. So we talked about those noble gases and them already having 8 valence electrons. Well, they satisfy the octet rule. And what the octet rule is that atoms are most stable with filled orbital shells. So they want to have filled shells, and what that means is they want 8 valence electrons. Now, elements with atomic number that are less than 36, they follow the octet rule. Okay, so they want to follow this, and that's generally everything that we deal with in general chemistry. That's everything. So they want to follow the octet rule. They like having 8 valence electrons. Now, an exception to that is just hydrogen and helium. They are stable with only 2 electrons, so they're happy with only 2, and that's because they exist in the 1s orbital, and so to completely fill that orbital shell, they just need 1s2, and they're happy. And that's why helium is a noble gas. It only has 2 electrons, and it's happy because that first energy level is completely filled, only having 2 electrons. Now, a Lewis dot diagram, or a Lewis electron dot diagram, what it is that chemists are often interested in valence electron structure of the atom. So how do the valence electrons play into everything? Remember that that is chemical bonding. That is our chemical bond. And so really valence electrons play a huge part in that. Now, the valence electrons are represented as dots. So when you're looking over here at lithium, that dot right here, that is representing a valence electron, and it's just around it. Now, electrons fill according to the Hund's rule, and we talked about the Hund's rule when we talked about electron configuration. And the Hund's rule says that every orbital will get 1 electron before it kind of gets 2. Now, the general order that we're going to teach you here, if we're looking at lithium, lithium has 1 valence electron, so guess how many dots it gets? 1. And then beryllium has 2 valence electrons, and so therefore it gets 2 dots, but we're going to put 1 at the top and 1 on the side. We're going to spread them out because everything's going to get 1 before it gets 2. And then boron is going to have 1, 2, 3. And then we see carbon, which has 4, 1, 2, 3, 4. And then we have nitrogen, so we'll go 1, 2, 3, 4, and then come back up with a second one for number 5. So let's look at our first example, the developing example. It says, draw the Lewis structure for selenium. So we find selenium on the periodic table, and we see that selenium is in group 16. So we know that selenium has 6 valence electrons. So we write selenium, and then we're going to put 6 dots. So starting at the top, 1, 2, 3, 4, 5, and 6. And that would be the Lewis dot structure for selenium. Our next one, the proficient level example, it says a new element is discovered with the Lewis dot structure of, and we see it down here, and it says, well, the question is, what chemical family does this element belong in? So if we're looking at it, how many dots does it have? Well, 1, 2, 3, 4, 5, 6. So it has 6 valence electrons, so it would be in group 16. That is our oxygen family, and so that's where it would belong. Now, jumping into the noble gases and start talking about why do things form ions and why do these things happen. The noble gases, they're in group 18. They're over here. See, we're pointing them out. It's that blue column. They already have 8 valence electrons. And so since they already have 8, they satisfy that octet rule. And so when we're looking at these, everything in chemistry, all elements are trying to become like a noble gas. And so we can use the periodic table to really help us out on figuring out ions, because everything wants to look like a noble gas. When I mean look like a noble gas, we're talking about their Lewis dot structure, or Lewis electron dot structure. So lithium wants to look like a noble gas. And so we'll see what it does here in a second. And that's our first group that we're going to talk about, is the alkaline metals. So when we're talking about the alkaline metals, they're over here, group 1 on the periodic table. And initially, they only have 1 valence electron. So they only have 1 valence electron. If we're looking at it, it has 2 choices. So we'll take sodium, for instance. Sodium, it's right here, it would have to gain 7, meaning go 1, gain 1, 2, 3, 4, 5, 6, 7. It would have to gain 7 or to look like a noble gas, or it would have to lose, so it would have to lose 1, and then it would look like neon. So it has an option. And normally, generally, elements are going to follow the path of least resistance. So what's easier? Is it easier to gain 7 or is it easier to lose 1? It's easier to lose 1, and that's why we say that the alkali metals will have a +1 oxidation number. They generally going to give up an electron so that it can have a +1 ion, be a cation, and lose an electron. Now we look at the alkaline earth metals. They're 1 over, so they're group 2. They're right here. If we think about magnesium, magnesium's right here. Well, is it easier for magnesium? Because generally, initially, it has 2. So can it gain 1, 2, 3, 4, 5, 6? Or is it easier just to lose 1 and then 2 and look like neon? Well, generally, it's easier to lose 2. And if it loses 2 electrons, it has a +2 charge. But it can, if we force it to, it can probably gain 6. Looking at group 16, so right here, if we're looking at it and look at oxygen, what's easier for oxygen to do? Gain 1, 2 and look like neon, or lose 6? Well, it's a lot easier to gain 2. And so when it gains 2 electrons, it'll have a not +2, but -2 oxidation number, because it's easier to gain 2 electrons to look like a noble gas. If we look at our halogens, so group 17, they're right here. These guys, all they have to go is 1 space over to look like a noble gas, so they're going to gain 1 electron, because it's a lot easier to gain 1 than it is to lose 7 electrons. So a cation, when we're looking at the periodic table, group 1, 2, and 3, and that should be 13, are more stable with less electrons. So when we're talking about group 1, group 2, and group 13, they're more stable with less electrons. And the reason why, if you look at the periodic table, we jump from group 1, group 2, all the way over here to group 13, we leave out the transition metals, because these guys have multiple oxidative states, and they got a lot of exceptions. So generally, we're talking about 1, 2, and then 13. Okay, so generally, they're more stable with less electrons. So if we give up 1, we have a full shell and we're happy. That's why lithium is more stable with a +1 charge. Now an anion, those are groups 15, 16, 17, are more stable with more electrons. And that's why we see that fluorine being in group 17, it gains 1 to look like a noble gas. So these are our charges that we have, and you can kind of write these on your periodic table. Really important to memorize this and have this down. So group 1 has a, and this is group 1, has a +1 charge, everything, all the way down. Group 2 is +2. Group 3, or sorry, 13, keep saying 3, 13 is +3, and this is 14. And that is, since it's right in the middle, what's easier to lose for or gain for? It can go either way. So it can be +4 or -4. 15, it's easier to gain 3. 16, it's easier to gain 2. 17, it's easier to gain 1. And then our noble gases, guess what? They don't have to gain any. So when we're looking at this, it says how many valence electrons does a stable, and this is a key word here, stable sulfur anion, and it's an anion, so anions are going to be negative, a stable sulfur anion have. So let's find sulfur, and we'll use our periodic table up here. We'll erase all of this. So stable sulfur anion. So if we look on the periodic table, sulfur is right here, and it's stable, so that means it looks like a noble gas. So what is it's done? It's gained 2 electrons, and now it looks like argon. So what we can say, since it started with 6 and gained 2, sulfur is now going to have 8 valence electrons. And the key thing here is sulfur having 8 valence electrons, it's stable. Anything that's stable is going to have 8 valence electrons. So that sulfur would be a -2 anion, and it has 8 valence electrons because it gained 2. Stable means that it satisfies the octet rule. The next one, which is the most stable? So we have fluorine with a, let me see, fluorine's right here with a -1 charge, chlorine with a -1 charge, bromine with a -1 charge, or iodine with a -1 charge. Now we're looking at the most stable. All of these guys, since they're all going to be our halogens and they all gained 1 electron, they're all going to be stable. And so what we would look at here is we look at what's the smallest. So usually when we're talking about distance from the nucleus, we know that fluorine is going to be the smallest. And so since it's the smallest and it has 8 valence electrons, it's going to be the most stable because it's the one that looks the most like a noble gas. Now, ionic bonding. When we think of ionic bonding, we want to think of Coulomb's law. And this is something that we'll kind of bring up, and you don't need to know all the details about Coulomb's law, but the main thing that we need to know is that opposites attract and likes repel. So when we're talking about this, we're talking about a magnet, and we've hopefully played with a magnet before to kind of look at it. Coulomb's law means that opposites attract. And so when there is a positive and there's a negative, we have a very strong attraction. And that's what we see in ionic bonds. Now, an ionic bond forms between a metal and a non-metal. So we would say left on the periodic table, right on the periodic table. So we look at our stair step on the periodic table. Everything to the right is a non-metal. Everything to the left is a metal. So that forms between a metal and a non-metal, an extremely strong bond, and it requires a large amount of energy to break it. That's why they have such high melting points, because it takes a lot of energy to break it. So when an ionic bond forms, some key things about it: it's solid at room temperature, very high melting points, very high boiling points, and brittle. Now we can look at this, and this is what is called a crystal lattice formation. And this little thing down here, you can kind of see the picture down here. And this is what an ionic bond looks like. You have all these positives and all these negatives because it's an attraction between a metal and a non-metal. And what happens is that metal, since it's more happy being a cation, which is positive, and that non-metal is more happy being a negative, well, if you could look at it, all these negatives are surrounded by positives, and all these positives are surrounded by negatives. And since you have all these positives surrounded by all these negatives, and that's what a crystal lattice is, think positives surrounded by negatives, because it's like that, it has a very strong bond. But if you can think this last part where it says that it is brittle, it's brittle because if we take this and kind of push this positive down, that means all these positives, basically all these positives and negatives that are going like this, you push Remember, that's a negative, that's a positive, that's a negative, that's a positive, that's a negative, that's a positive. Well, if we push it down just one, what we'll see is then we have, we have all these negatives and positives lining up. And remember, like repel, and so they kind of break apart. So we say that they're brittle, but they're very strong bonds. So let's look at an example. Which of the following are ionic compounds? So when we look at this, we look on the periodic table, and we look and we see, is it a metal and is it a non-metal? So if we're looking at this, calcium is on the left side of the periodic table. Chlorine is on the right side of the periodic table. So therefore we have an ionic bond. We have nitrogen, which is on the right side of the periodic table, and dioxide, oxide would be oxygen, it's on the right side of the periodic table. That means it's two nonmetals. That is not an ionic compound. And then lastly, we have carbon, which is on the right, and tetrachloride, which is on the right. And so therefore we have two rights, two nonmetals, and guess what? That would not be an ionic compound. Another telltale sign, anything that has dioxide, tetrachloride, these prefixes like this, generally those guys are going to be covalent compounds, and they are not going to be ionic compounds. Look at our next one. It says develop a method for testing different substances to determine if they are ionic compounds. Well, one method when we're looking at these, remember that they have very, very high melting points. So what we could do is we could test the melting points of different substances, and if they have a really high melting point, we know that they're an ionic compound. If they have very low melting points, then we know that they are not an ionic compound.